Remember, whether we're encrypting messages by hand or through the use of computers, encryption requires two things. It requires us to have a cipher, or the set of rules that you're using to encode the information, and we also need the key. And this is how we arrange those rules. So, for example, I can use a Caesar cipher, which allows us to shift the letters of an alphabet up or down a certain number of letters to encode a secret message to you. After choosing the method by which I want to encrypt my information, all I need to do is decide on the key. In this case, I choose to shift the alphabet by 13 steps. By shifting the cipher by 13 steps, a message that says hello will now read URYYB. If I handed that secret message to you, it would be your turn to decrypt the message. You could decrypt it in two ways. The first and easiest way would require you to have access to the kind of cipher and key that was used to encode the message in the first place. In this case, you would need to know I used a Caesar cipher and that I shifted the alphabet up 13 letters. Reversing the process from that point should come very easily to you. Or, if you only had the encoded message with no additional information, you could crack the code by using brute force, or you could analyze the code and work backwards to decipher it. Since a Caesar cipher was used to encode the message, the process of deciphering would only take a short while for you to decrypt, even if you didn't have a cipher or the key. Modern-day encryption is no different than the types of encryption exercises you've learned in this lecture and in our homework. The only difference is, instead of using something like a Caesar cipher as the rules for encoding information, your computer uses something more complex, an algorithm. The key, or the way that you need to arrange those rules when you're dealing with modern-day encryption, is a piece of information that works with the algorithm to determine the output. When you encrypt data, one of the most important aspects of deploying ciphers is the size of the key. When a key is very long, it takes a very long time for a computer that may intercept the encrypted information to decode. It is very common that when we're talking about the strength of a crypto system, that we refer to the size of its key. So how does modern-day encryption work? Well, in a few ways. Modern-day cryptography is often grouped into two broad categories that are associated with the types of keys that are being used for encryption and decryption operations. This was mentioned to you in the code.org video that you viewed just a little while ago. These two groups are known as symmetric encryption and asymmetric encryption. Let's take the time to discuss both. Symmetric key encryption is also known as private key or secret key encryption. This requires the same secret key to be used when someone enciphers and deciphers a message or a piece of data. In order for this type of encryption to work, the sender and receiver must both possess that secret key. Symmetric encryption methods can be extremely efficient, requiring minimal processing to either encrypt or decrypt a message. However, the problem is that both the sender and the receiver must own the encryption key. If either copy of the key is compromised, an intermediate can decrypt and read the messages that are being sent. One of the challenges of symmetric key encryption is getting a copy of the key to a receiver, a process that must be conducted out of band to avoid interception. Some examples of symmetric key encryption are DES, or the Data Encryption Standard. DES was originally designed by IBM in the 1970s in response to a call for a federal standard for encrypting non-classified information. In 1976, this was adopted as our nation's encryption standard. After DES came a few other iterations of symmetric key cryptography. Triple DES, also known as 3DES, was created to provide security far beyond DES. The Advanced Encryption Standard, or AES, was created to replace both DES and 3DES. AES is popular in symmetric key cryptography and is still being utilized today. AES has become the dominant symmetric encryption algorithm in use today. We discuss DES in the book both for historical purposes and because it is a relatively simple algorithm to use to explain how this type of cryptography works. It's very important for you to review your materials to see how these work and how they differ in practice. By now, we've recognized that symmetric key encryption is not the safest means for protecting our information. So, how do we manage to safeguard sensitive data without the worry that someone will intercept our private keys? The answer lies in asymmetric encryption. Asymmetric encryption, otherwise known as public key encryption, is a way by which we encrypt and decrypt information through the use of two different but related keys. Instead of two users sharing one secret key, each user has two keys, one public and one private. Asymmetric encryption is most valuable when messages encrypted using the user's public key can only be decrypted using the user's private key, and vice versa. As our code.org video showed us, it's really easy to visualize asymmetric encryption. Let's pretend that Alice has a mailbox that's locked on the outside in two places. On the top, members of the public with the correct key can open up the box and put mail in the slot for Alice to read. But only Alice can remove the mail from the box using the private key that is only owned and used exclusively by Alice. Just as this illustration shows, a public key is something that is shared with everyone who wishes to send information to Alice. Public keys can be distributed to the general public or just to a few people. This is completely up to Alice and will not destroy the integrity of the encrypted messages. There is no way that the message can be decrypted unless that person has access to Alice's private key. Symmetric and asymmetric algorithms have complementary strengths and weaknesses, and are therefore used both for different purposes and in concert with each other. The book goes into detail about the two types of encryption in relation to each other. By now, we've covered so much information about how we encode and decode information between computers and through encryption. Our readings, videos, and homework show us just how complex this system of encoding and decoding messages truly is. While encryption can help us safeguard the data that we're trying to protect, there are still many other things that we must be concerned about as we send data between different computers and devices. Namely, how can we verify that the data is not corrupted? Or how can we verify that the true identity of the sender is preserved in transmission? These concepts of integrity and non-repudiation need to be addressed through other means. In order to answer the two questions, we must find a way to combine encryption with other important methods to make it most effective. First, we must think about hash values. Hash values are a way that we can verify that our data has not been corrupted in transit. A hash value is not an encryption algorithm, nor is it an authentication method. It is instead something entirely different. In your required materials for this segment, I've included another Linda video that shows a thorough and creative example of how hash values work. If even the smallest change in data is detected, the resulting hash value will be different than what you began with. Now that we have an idea of how we can verify the integrity of the data, how do we verify that the person who sent the data to us in the first place is who they say they are. The way that we can verify this information is through the use of digital signatures. Digital signatures were created as a response to a rising need to verify information that was transferred over electronic systems. The way that these are implemented are through asymmetric encryption. Let's watch a short video about what digital signatures are and how they function.